Measuring the steepness of a curve at every coordinate does not guarantee those slopes transition into one another without interruption. This is a fundamental rule of calculus, presented here in Theorem 5.2 of Walter Rudin's text. It establishes that if a function is differentiable at a point, the function itself is absolutely continuous at that point. For a function to be continuous shows the standard intuition for this behavior. When a curve has no sharp points, we expect its tangent line to glide along the path and map out a second, equally smooth graph of the derivative values. Functions that satisfy this expectation are called continuously differentiable, or C1. This classification requires both the existence of the derivative and the continuity of the derivative function itself. However, the existence of a derivative at every point is a separate property that does not actually require the resulting derivative function to be continuous. When we rely strictly on visual intuition, we overlook the specific ways the real number system allows functions to behave pathologically. We need to define how a slope can be calculated for every coordinate, even if the sequence of those slopes is fractured. To demonstrate this, we must construct a function that is perfectly unbroken and differentiable everywhere, but whose derivative fails to reach a consistent limit at a specific coordinate. Basic polynomials and trigonometric functions are too structurally stable for this demonstration. Their derivatives are always as well behaved as the functions themselves. Locating the exact point where these properties diverge requires testing the formal limits of the difference quotient against our visual expectations. This foundational anomaly is listed in Rudin's text as equation 7. It defines a piecewise function where f of x equals x times the sine of 1 over x. This chart shows the function approaching the origin. Because the squeeze theorem clamps the oscillating wave between the lines y equals x and y equals negative x, the function is forced to converge to 0, proving it is continuous at the center. If we anchor a secant line at the origin and move its other end toward the center, the slope of that line begins to thrash wildly as it follows the oscillations of the sine wave. The slope of this line swings infinitely between +1 and -1, never settling as x gets smaller. Because this oscillation continues forever, the formal limit of the difference quotient does not exist. This confirms that the function, while unbroken and continuous, is not differentiable at x equals 0. By dampening this oscillation, we can force a single finite derivative to exist at the origin. To do this, we multiply the function by an additional factor of x. This gives us equation 9, f of x equals x squared times the sine of 1 over x. In this chart, the chaotic oscillations are now flattened by parabolic bounds. This stabilization allows a tangent line to form at the center. According to the definition of the limit, the derivative at x equals 0 now exists and is equal to exactly 0. For every other coordinate on the line, we can determine the derivative using the standard product and chain rules. This calculation results in equation 10. For any x not equal to 0, the derivative function is 2x sine of 1 over x minus the cosine of 1 over x. The first term of this derivative effectively vanishes to 0 as it approaches the origin. However, this diagram shows the second term, negative cosine of 1 over x. This term retains an infinite oscillation between 1 and -1, regardless of how close we get to the y-axis. This creates a total disconnect. While we know the slope at the origin is 0, the slopes immediately surrounding it never settle on a value to meet it. This function has a defined slope at every single coordinate, yet the derivative function itself is fractured and discontinuous at the origin. If derivative functions are permitted to be discontinuous, are there rules governing how they break? For example, a derivative function cannot have a clean jump, a discontinuity where the graph simply restarts at a different height. This is Theorem 5.12, Darboux's theorem. It dictates that a derivative must take on every intermediate value between any two of its slopes. To prove this, the text constructs an auxiliary function, g, designed to force a local minimum. At this forced minimum point, the derivative of that auxiliary function must be 0. This condition mathematically forces the original function's derivative to hit the exact intermediate value required by the theorem. Physically, this means a derivative cannot transition from one slope to another without passing through every fractional slope in between. This constraint is why our previous example was forced to oscillate infinitely. It was the only way for the derivative to be discontinuous without violating Darboux's theorem. Any discontinuity a derivative suffers must be an infinitely dense oscillation, because a clean, jump-style break is fundamentally impossible. Differentiability proves that a curve is connected, but it does not guarantee that the derivative of that curve is connected. Visualizing this hierarchy, outermost C sub 0 represents unbroken functions. The middle tier represents differentiable functions. Innermost C sub 1 represents smooth functions. Our counterexample is barred from C sub 1. This distinction is critical in physics and differential equations, where models often require the stability of the C sub 1 classification. Relying on differentiability alone leaves a model vulnerable to the unresolvable oscillations and microscopic chaos we have identified. A curve can have a specific tangent at every coordinate, without those tangents actually forming a smooth, continuous sequence. Rigorous analysis proves that a function can possess a strictly defined slope at every coordinate, even while the sequence of those slopes remains fractured. To continue exploring the rigorous logic and pathologies found in texts like Principles of Mathematical Analysis, subscribe to the channel. In higher mathematics, visual intuition is only the first step toward the truth.